Hey, Vlad here, DevInsider.com. Welcome to another video. So I was looking at my potential videos list, trying to figure out which topic to cover next, and spontaneously picked up Graal without realizing that it would take me down a rabbit hole of 4 full days of research. So today we're going to learn new words, talk about virtual machines, compilers, interpreters, optimization techniques, and even legal issues like licensing. In case you are new here, you should probably know that this is mostly a Scala channel. However, we're not writing any code today, so no worries. Having said that, even this video is going to be Scala flavored because Scala developers can and should immensely benefit from Graal. Before we begin, I would like to point out that you see how long this video is and you chose to click on it anyway. There will be a lot of information in this video and you might deem some of it as unnecessary. This is just a style of videos that I like to make, so even though I could have explained Graal to you in just a couple of minutes, I chose not to do it. If you're busy, check out the time codes in the description below and feel free to skip some parts. Alright, there are 3 goals that I have for this video, and in fact it was super hard for me to choose the title for this video because there's so much information that I simply didn't manage to split into several parts. Number 1. Graal is an overloaded term and the surrounding technologies are being actively developed, so getting into the Graal ecosystem might be a little bit challenging or confusing. At least this is how it was for me. And so the first goal is for you to be able to pick up a blog post about Graal or a YouTube video and at least be able to figure out which part of the ecosystem they're talking about and at least not to feel lost. Don't get me wrong, we will cover so much information that you won't feel the need to do any research on your own. However, having said that, the technologies around Graal are being actively developed, so there is new information almost every day. My second goal is to show you which benefits you get as a typical Scala or even Java developer. However, I will not show you any of those because the next couple of videos are going to be about Graal as well, and they will be a little bit more hands-on. My third goal is targeted towards the typical Graal audience, the people who are trying to save some money by squeezing out more performance and wasting less resources in Java applications. Let me also point out that I have no relation to Oracle, so take everything that I say with a grain of salt. I simply spent a couple of days researching this topic, and so I might have misunderstood a thing or two. If you spot a mistake, please let the people know in the comments below. We're all just trying to learn here and improve the developer inside you. Alright, we're going to start at the very beginning of the Java history, and we're constantly going to be stumbling on fancy new words, which I will explain as we move along, except for 2 very important ones, which I will explain right now, and trust me, we're going to need them. A lot. These words are static and dynamic, 2 adjectives that describe time. A computer program goes through many stages before it finally runs. The things that are being done to the program before it finally runs, aka dev time, are set to be static, and the things that are being done to the program after it's deployed, aka runtime, are set to be dynamic. Let me give you a few examples. The first and the most canonical example is in the realm of type systems. A type system is a system of proof. All a type checker does is proving that the type of the value on the left-hand side of the equal sign equals to the type of the value on the right-hand side of the equal sign. A static type checker does its thing before the runtime, and a dynamic type checker does its thing at runtime. A bit of side information here, the type checking adjective is commonly falsely attributed to the programming language instead of its execution engine. For example, Java or Scala are statically typed, or Python or JavaScript are dynamically typed. However, this is not entirely correct. Languages like Java and Scala are said to be statically typed only because the compiler, which is a tool that translates a higher language into a lower one, decides to check the types during one of its phases. One could write an interpreter for languages like Java and Scala, which is a tool that translates a higher level language into machine code on the fly, and then these languages would all of a sudden magically become dynamically typed. The reverse is true for languages like Python. In fact, it is not uncommon to compile Python down to a language like C and thus making it statically typed. This slight detour brings us to our next example, which happens to be in the realm of compilers and interpreters. Compilers are almost by definition static because compilation happens before runtime. In fact, compilation is sometimes being referred to even more explicitly by calling it ahead of time compilation, and time being the runtime. So it's ahead of runtime compilation. Interpreters, on the other hand, are almost by definition dynamic because they interpret their code on the fly. This is sometimes called just-in-time, just-in-runtime interpretation, not to be confused with just-in-time compilation. We're not there yet. Now, both compilation and interpretation have a lot, and I mean a lot of gray zone between them, because these days compilers and interpreters work hand in hand, and we will see this in just a bit. Essentially, some compilers can interpret pieces of code, and some interpreters can compile pieces of code to achieve better performance, so the lines are kind of blurry. Another slight detour here: even though technically this is not mandatory, dynamic languages are typically interpreted and static languages are pretty much always compiled. Our last example is lurking in the realm of linking, which is technically a compiler-related concept, but as I just said, the lines are kind of blurry these days. Static linking means that once the program is linked, all the resources are known, which is again related to ahead-of-time compilation, or in this case technically ahead-of-time linking. Dynamic linking, on the other hand, means that the program might receive some resources at runtime, and even though this sounds like magic, in the real world it is actually happening all the time. You might have seen messages in the .NET aka Windows world telling you that your program couldn't start because some DLL was not found. Or in the Java world, you would see messages telling you that some class was missing from the class path. For instance, if you use the Scala compiler to compile a Scala class containing a very simple Hello World project, it will obviously compile. However, once you start running it on the JVM, it will fail, telling you that it can't find Preda because the entire Scala standard library is missing from the class path. We're slowly approaching the main content of this video, but please remember this part, because even though most, if not all, Java developers remember that Java's goal is to write program once and run them everywhere, this so-called platform independence is only one of Java's 3 main goals. Another goal was security. Java's programs run in a managed environment in the so-called Java virtual machine, which is, by the way, the centerpiece of this video. Security is provided via the concepts like checked exceptions, automatic memory management, security managers, and even the fact that Java, the language, is more type-safe than C++. Having said all that, security is not relevant for the rest of this video, and so we're not going to talk about it anymore. The last of the 3 goals, however, is worth mentioning, and it is network mobility, the only goal that happens to be forgotten very often. There are 2 parts related to this network-oriented agenda, the first being RMI, or Remote Method Invocation, a concept which allows you to call a method on a distant virtual machine. It didn't find mass adoption though. The other side of the network coin is way more interesting, and it is related to dynamic linking, which we just learned about. Even though Java is a statically typed, mostly compiled language, it is dynamically linked. This means that you could load Java classes which potentially reside on distant virtual machines at runtime, or you could simply use language features like reflection, which load classes dynamically, aka at runtime. Now, even though there are a lot of Java applications out there which use reflection, which they probably shouldn't, but loading classes from the network is not as common as you might think. However, I really needed to mention it here because this is pretty much the only reason why Java applications are not allowed to run on iOS. Apple wants to see all of your code ahead of time. It simply does not allow you to load code dynamically from some distant server at runtime. Now, as a typical Java or Scala developer, you might not care about iOS. However, I highly advise you to stick around until the end of this video, because by the end we will run full circle and we will see how in the very near future you will be able to run native Scala apps on iOS without having to transpile them to JavaScript first in order to use frameworks like React Native. Alright, let's talk about Java, and by that I mean everything else but the Java programming language. So we're talking about the Java virtual machine, or the Java runtime environment, which is the Java virtual machine and the standard library, or even the entire Java development kit, which is the Java runtime environment, plus the Java compiler and a handful of other development tools. The JDK was created in 1994 and released by the end of 1995, and a couple of bug fixes later, the stable version came out in the early 1996. It was created by Sun Microsystems and it was written in C++. The Java-C, the Java compiler, would translate the Java source code stored in .java files into the so-called bytecode, which is stored in .class files and typically bundled in the so-called jars, Java archives. The Java runtime environment, or the JRE, which again consists of the JVM, or the Java virtual machine, and the standard library, would take your application and dynamically link it with the standard library. The JVM would then go ahead and start interpreting the bytecode of your application, which means on the fly translating it into machine code, or at least into assembly code. The Java runtime environment, or let's just say the Java virtual machine, would run either on the client's device or on one of your servers. One thing to note here is that the concept of virtual machines dates back to 1972, so the Java virtual machine was not the first one. However, I'm mentioning this here because at some point it became open source, and even to this day there are a couple of alternatives, and we will talk about some of them, but we will mostly stick to the Sun/Oracle lineage. Let's go back to the history lesson. This is not a well-known fact, but interpreters are actually capable capable of optimizing their code at runtime, just in time. Again, do not confuse this with just-in-time compilation. We're not there yet. Now, sometimes interpreted programs can run faster than statically compiled ones, but these are merely exceptions. Most, if not all of the times, the statically compiled programs win in terms of performance. And so the typical complaint of Java was that it was slow. There are two parts of the JVM that could be tweaked, the interpreter and the garbage collector. The garbage collector has been rewritten quite a few times since then. However, garbage collection is not important for the rest of the video. The canonical way for improving interpreters is simply putting a compiler on top of them. This is called just-in-time compilation, and we're going to talk about it quite a bit. By the end of 1998, the second version of Java came out, and it included not one but two just-in-time compilers, which were hidden under an experimental flag, which will be a common theme for the rest of the video. Let's ignore the fact that there are two compilers instead of one for just a second, and no pun intended. The goal of a dynamic or a just-in-time compiler is to increase performance of an interpreter. It does that by compiling chunks of bytecode into machine code of the targeted platform. And I wish that I could tell you that this is the end of the story, but unfortunately, things are not so simple. In fact, this is just the beginning. The strength of just-in-time compilation is also its weakness. See, the problem is that you don't know the platform ahead of time. Is it going to be Windows, Mac, or Linux? Is it going to be a big machine or a small machine? Remember that the vision for Java was to be able to run anywhere on small pages or even PDAs, the personal digital assistants, and that whole thing happened long before smartphones. In any case, we're talking about a dynamic compiler which has to compile code at runtime, just in time. So if you wanted to just in time compile all the code of your application, we would have to do it every time the application starts. This is unacceptable, especially for client-side applications. Luckily, it is estimated that only 10% of your methods are the ones that are being called 90% of the time. And so the interpreter interprets your code right away, but it also keeps track of how often it calls your methods or how often it goes into certain branches. So it gathers this profile information, which is collectively called as the warm-up phase. Once a configurable threshold is reached, the interpreter makes a decision to optimize this particular method or branch by asking the just-in-time compiler to compile it into machine code just in time. I would like to stress this point again, that merely compiling something is an optimization technique in its own right. While this method or branch is being compiled by the just-in-time compiler, the interpreter does not wait. The interpreter and the compiler race until who finishes first, and then eventually the compiler comes back to the interpreter and says, here you go, this is your method, I compiled it. And then eventually the interpreter switches to the compiled version, which lays in its cache. This technique is called adaptive optimization. So the just-in-time compiler tries to adapt to your application and find its hotspot. It's these 10% of the methods that I was talking about just a bit ago. The so-called warm-up phase is also the reason why benchmarking Java applications is such a pain in the neck. You have to wait until your application is warm before you can start with your benchmarks. By the way, the fact that these benchmarks work at all is due to the following fact. The hotspot of your application might move around a little bit. However, once the JVM is warm, meaning its cache is full, it is not going to be refilled. Or in other words, the interpreter will simply stop asking the just-in-time compiler to compile things. The JVM is considered warm at this point, or should I say, hot. I'm actually not 100% sure about this point though, so take it with a grain of salt. But then again, if I'm wrong, then how do you benchmark Java application? Sure, you could turn off all the just-in-time compilation, but that's just not the same. In any case, let's get back to the story in which the name hotspot was up for grabs and Sun snapped it under everyone's nose. In Java 3, which came around the year 2000, these compilers were enabled by default and the entire virtual machine was labeled the hotspot virtual machine. Just as a reminder, there are alternative VMs out there and we will get to them in just a second. Now, before we discuss why there are two just-in-time compilers and which one of them is actually enabled by default, I would like to point out a relatively unknown fact even in the Scala circles. Martin Odersky, the creator of Scala, has written the second version of the Java compiler, which became the default compiler since Java 3. We're talking about the Java C compiler, the one that translates your Java source code into bytecode, and not the two just-in-time compilers that we just introduced. Another fun fact, Martin's Java 3 compiler already had generics, which were disabled all the way until Java 5, which came out 5 years later. Alright, back to the story. So why are there two just-in-time compilers and not just one? Well, these two compilers employ different optimization techniques. The first compiler, called the C1 or the client compiler, is a very lightweight compiler. Since I'm not a compiler guy, allow me to read a passage for you straight from the so-called HotSpot glossary. Fast, lightly optimizing bytecode compiler, performs some value numbering, inlining, and class analysis. Uses a simple CFG-oriented SSA, high IR, which probably stands for intermediate representation or something else entirely, a machine-oriented low IR, a linear scan register allocation, and a template-style code generator, whatever all of that means. Its purpose was to be used for client-side applications, meaning desktop GUIs or command line interfaces. So it would make the trade-off to not optimize, meaning not to compile too much, because if it did that, the application would take forever to start up, which is unacceptable for a client-facing application. In fact, my very poorly funded research tells me that the macOS and Windows versions came only with this one client compiler, because these operating systems, even to this day, are mostly used for client-side applications. The Linux version of the HotSpot VM, on the other hand, came with both compilers, the C1 or the client compiler and the C2 or the server compiler, also known as Opto. Yes, Opto. Don't ask me why. The C2 or server is a way more aggressive compiler with much higher default compilation thresholds and therefore much higher startup times, which is fine for a server which might be running a couple of days or even a week. I'm reading again from the glossary. Highly optimizing bytecode compiler, also known as Opto, uses a C of nodes SSA ideal IR, which lowers to a machine-specific IR of the same kind, has a graph coloring register allocator, colors all machine state including local, global, and argument registers, and stack. Optimizations include global value numbering, conditional constant type propagation, constant folding, global code motion, algebraic identities, method inlining, aggressive, optimistic, and or multimorphic, intrinsic replacement, loop transformation, unswitching, unrolling, array, range, check, elimination. Now, I'm not a compiler guy, so I don't know what most of these things mean, but it sounds very serious, that's for sure. Now, we're going to bunny hop through history a little bit in order to speed this up, and so I will cherry pick the pieces that are relevant for Graal, which we haven't even arrived at yet. The next part is filled with relatively boring, but unfortunately necessary to understand legalities. Thanks to the HotSpot VM and Martin's new compiler, Java became really popular in the early 2000s. However, parts of the JDK were proprietary pieces of software which became known as the Java trap, which became popularized by Richard Stallman's article in 2004 called Free but Shackled, the Java trap. I don't want to bore you with the details, but the offshot is this. Between the years 2006 and 2007, most of Java became open source except for a few parts. Sun wanted to create alternative implementations for these closed source parts. However, Red Hat beat them in the same year with a project called Iced-T. By the end of 2007, Sun finally managed to open source the remaining parts under the name OpenJDK. In fact, the Red Hat guys tried to snap the same name, but it was trademarked by Sun, and so they picked up some other beverage-related name like Iced-Tea. Pretty much right away in 2008, Red Hat, the Iced-T maintainers, which still exist to this day by the way, started contributing back to the OpenJDK. Both of these, the Iced-T, which is pretty much irrelevant for the rest of the video, and the OpenJDK are free and open source under the GNU General Public License with the ClassPass exception, which I'm not going to get into at all. So again, there is Iced-T, which is pretty much irrelevant for the rest of the video. There is OpenJDK, which is also free and open source. Then there is a JDK from Sun, simply called the Java Standard Edition or the Java SE, and an even more proprietary version of Java also from Sun called the Java Enterprise Edition with an even more optimized C1 and C2 compilers, which we're going to get back to in just a few seconds. In the beginning of 2010, Oracle acquired Sun, and so the JDK is also called the Oracle JDK. Java 6 came out in 2006, and yes, we skipped quite a few Java versions which are irrelevant for this video. In fact, the only reason I mentioned Java 6 is to remind you that it took 5 very long years for Java 7 to be released, which happened in 2011. I'm mentioning this because this was the time when creating alternative JVM languages became almost a national sport. Languages like JRuby, Groovy, Clojure, and Scala were all created around that time. To be clear, they were created even before 2006, but this was the time when they actually became popular. Anyways, Java 7 came with the ability to stack the C1 and the C2 compilers on top of each other. This is called mixed mode or tiered compilation, which became the default in Java 8, which came out in 2014. Chances are that you, like me, are still on Java 8, and so if you type java-version into your console, you will see mixed mode written somewhere in the output, and you can also turn it off if you like. The goal for mixed mode compilation was to gain the best of both worlds, faster startup times than with C2, and more optimization than was just C1. The idea was also that each tier would add more profiling information, and so once the code finally reaches the C2 compiler, it will have, first of all, less to optimize because some of the code was already compiled by C1, and it would have more profiling information to make better decisions. In fact, the C1 compiler runs several times and collects varying degree of profiling information. So we have the tier 0, which is just the interpreter, then we have the tiers 1 to 3, which is C1, and then on top of that we have tier 4, which is C2 or the server. Understanding the tiers 1 to 3 is not really important for this video. Now we're almost ready to talk about Graal, but unfortunately we have to digress again and talk about the two things that Oracle did very recently. The first thing they did was speeding up and streamlining the release process for Java, which sounds good on paper, but hold that thought. Starting with Java 9, which came out in September 2017, each new Java version will come out every 6 months, every September and every March. I'm recording this video at the end of September 2019, and Java 13 came out just a couple of days ago. Coincidentally, Scala 2.13 also came out a couple of months ago, but there is no relation whatsoever. This is just a coincidence. By the way, since Java 9, the JRE, or the Java Runtime Environment, is not available for download separately, so even though if you're not a developer, you're pretty much forced to download the entire JDK. I guess that's done just for simplicity, because now they have to release every 6 months. Anyways, as a developer, this all sounds very awesome. However, if you have a company to run, you pretty much never want to switch Java versions as often as shoes. Oracle, as many other companies, is aware of that, and so every 3 years a so-called LTS or long-term support version will come out, which will be supported for up to 7 years. Sounds promising, right? Well, remember that just a second ago I told you that Oracle changed two things. The one we already discussed, the streamlining of the release process. And the second one is what I like to call cash milking, and by cash, I mean money. Beginning with April 16, 2009, you have to pay for Java for development of commercial products, or if you want to run Java on the server. Running it on a desktop is fine from what I'm reading. At this point, I would really like to point out that I'm not a lawyer, so please don't make any purchasing or, in fact, any other decision based on anything I say. Now, even though Java 8 was released before that date, this licensing change indeed applies to Java 8 depending on the minor version that you're using. And Java 8 was also deemed a long-term support version, which runs out in 2020. And so this whole LTS mambo jumbo that I was talking about only applies to Oracle's premium customers. So what are your options? Option 1, use the OpenJDK. It has pretty much the same features and the same release schedule, but there are no LTS versions. Your second option is to use the project called Adopt OpenJDK, available at adoptopenjdk.net, and this project is backed by a bunch of really big companies like Amazon and IBM and whatnot. It offers both regular and the LTS versions of the OpenJDK with support for up to 4 years, and you can even choose an entirely different VM. There's HotSpot and there's IBM's V9, and if you really need commercial support, they got you covered as well. Alright, why did I bore you with all of these legal issues? Well, the thing is that Graal was created by Oracle. No worries, there's a free version as well. Essentially, when I started researching Graal, I realized that it's not just one thing that was released at some point. It's a lot of moving parts, and some of them are not available in every version of JDK and so on. Anyways, let's finally start talking about Graal. Somewhere around 2011, which is shortly after Oracle's Sun acquisition, Oracle Labs, formerly Sun Microsystems Laboratories, or Sun Labs, which is a research and development branch of Oracle Corporation, started to work on a project called Maxine VM, which coincidentally or not was right after Java 7 was released, and as we just discussed, Java 7 brought tiered compilation. Maxine was supposed to be a sandbox for experimentation on virtual machines. The goal of such experimentations is usually to squeeze out more performance out of VMs. In case of Maxine, there was a secondary goal, however. The C++ code bases of the entire virtual machine and the C1 and C2 compilers were 15 years old at this point, and they gradually became harder and harder to maintain. So what they tried and succeeded with was creating a so-called meta-circular virtual machine, which is just a way of saying that the Java virtual machine that they created was written itself in Java. Now, that worked out just fine, and so they kept going. They took the C1 compiler, which was written in C++, and they ported it to Java, and they called it C1X. All this quite successful research is fine and dandy, but what about practice? What about the HotSpot VM that is written in C++? You have the Maxine VM, which is written in Java, and you have the C1X compiler, which is written in Java. How are you going to integrate it now with the HotSpot VM? And so they created another project called C1X for HotSpot. And the purpose of this project was supposed to be, and I'm going to repeat this, it was supposed to be to integrate the C1X compiler into the HotSpot. But they stumbled on the Holy Grail. I'm reading from Oracle Docs. The Maxine project Graal. The holy quest of this project, formerly named C1X for HotSpot, is to integrate the Java port of the C1 client compiler called C1X back into the HotSpot JVM. The compiler runtime interface CRI enables one compiler to work in different VMs. This part is very important, by the way. The details of the CRI are explained in a VEE 2010 paper available in publications. After the initial goal was achieved, we started asking ourselves the question: what would it take to make C1X into a compiler that generates code of a quality comparable to or better than the server compiler in HotSpot? In an effort to explore this question, we branched off from the C1X codebase and started adopting a new compiler design. The name Graal now applies to this new compiler, and its integration into HotSpot is called the GraalVM. Before I continue reading, I would like to point out that the term GraalVM has been rebranded quite substantially since then. The paragraph that I'm reading is over 6 years old. Let me finish it real quick. The initial development of Graal has been performed in the context of both HotSpot and the Maxine VM. The source code for the compiler itself is part of the Maxine Mercurial repository. This initial development has convinced us of the potential of Graal to improve the performance and extensibility of both VMs. In order to expedite the development of Graal, we have now decided to focus on one VM. HotSpot. From the perspective of Maxine, this means that Graal source code it includes will not be changing or evolving in the meantime. End of quote. Now there are 4 things that we need to get from this. 1. Forget the C1X compiler. 2. Graal is essentially the new C2X compiler, right? So this is a tier 4 compiler. Its primary purpose is tier 4 compilation of bytecode into machine code. 3. In order to integrate Graal into the HotSpot VM, which is written in C++, we first need to create a compiler interface for the interpreter, which is written in C++ to consume, and for a compiler written in Java like Graal to implement. And 4. Everything that I say from now on technically applies starting from Java 9. However, since most of the planet is still on Java 8, there is also a version of Java 8 with all of this good stuff backported. So you can start reaping benefits from Graal right away, and a bit later in the video I will also show you how. Alright, now before I continue, I would like to point out that the entire Java ecosystem has really high hopes for Graal, which is also why it's called like this. And so everybody's trying to use and abuse and build on top of Graal. It's pretty much insane. Google Project Metropolis if you're interested, and I will also say a few things about it a bit later in the video. Alright, so if you want to mentally shut off for a bit, feel free to do so. Just remember that for you, the typical Scala or Java developer, Graal is primarily used as a replacement of the tier 4 C2 compiler. Alright, Java has this thing called Java Enhancement Proposals, or short, JEPs, and we're going to go through 3 of them real quick. Coming right up, the JEP 243, Java Level JVM Compiler Interface. This is where Java's dynamic nature becomes super useful, because what you can do now is the following. You can download Java 9, you can download the source code of Graal, which is mostly open source and it's on GitHub. You can add a few print lines to it, you can publish it locally, you can add a few configuration flags to the JVM, which will now be able to talk to Graal, right? This is very, very important, right? You did not need to build your own Java 9. You just built your own compiler, and now there is a way to connect it to the JVM. All because of dynamic linking and the JVM Compiler Interface, of course. Now, even though you don't need to do any of that anyway, but if for some reason you still want to start with Java 9, you would need to enable 3 flags. The first one would enable experimental flags in the first place, because at the time of Java 9, this whole thing was experimental. The second flag would be to enable the Java Virtual Machine Compiler Interface, and the third flag would specify the Java Virtual Machine Compiler Interface compiler. And most of the cases, you don't actually need to specify its name, because you're just going to have Graal on the path anyway, probably. By the way, this is not the class path, this is a module path. It's a different thing. Anyway, you probably don't want to know this. Alright, the next JEP is the most confusing one, and in fact, I believe that pretty much the only reason for it was to sneak the Graal compiler into the JDK as soon as possible. It's the JEP 295 ahead of time compilation. Now here's the thing. So we have this Java Virtual Machine Compiler Interface, and we could manually add Graal to it to be used as a tier 4 compiler. However, this is not what is happening in this JEP. What happens here is that Graal was added to the JDK, but for a completely different purpose. It was in there to create another tool called JAOTC, which stands for Java Ahead of Time Compiler. So if you have JDK 9 installed, you will look in there and you will have your Java CN and friends, and you will also have this new tool called JAOTC. Now this is the tricky part, so listen carefully. So what you can do now is, if you know that the system where you're developing is going to be the same one as your target system. So for example, you're developing on Ubuntu 18.04 and you're also deploying to Ubuntu 18.04. And if you're using exactly the same JDK on both of these platforms, then you can do the following. You can use this tool to ask it to compile specific parts of your Java applications ahead of time, right? And you can deploy these parts as well with your applications. And these parts, you can specify for the just-in-time compilers to use as sort of like another partition of its cache, right? So the idea is that, for example, you have a small application and it uses the Java standard library and maybe, I don't know, Spring or something, right? So you use this tool to compile the standard library and Spring ahead of time, right? You deploy it together with your application. You tell the JVM to use it as basically like a, you could think of it as an extra partition for the cache of the just-in-time compiler. Remember, the just-in-time compiler has a cache, right? So this speeds up the startup and it lowers the footprint, the memory footprint of your application and so on. By the way, very, very important, if you're familiar with native image from GraalVM, that's not it. It's a similar thing, but that's not it. We're going to get to the native image in just a bit. Now, in case this is confusing, hold on tight because it gets even more confusing, because what we can do is we can use Graal, or we can use the Java Ahead of Time compiler that uses Graal to compile Graal itself ahead of time and use it with your JVM. Right? Because remember that when the JVM starts up, it starts up this warm-up phase, right? And it uses the C1 and the C2 compilers to warm up. However, if the C2 compiler itself is written in Java, then it itself needs to warm up, and you might not want them. So you might be interested in compiling Graal itself ahead of time and using it as a tier 4 compiler. Now, all of this ahead of time mumbo jumbo is pretty much still experimental, so you can pretty much forget all of it except for two things. If you really want to use Graal with Java 9, which these days you probably shouldn't, all you need to know is that you need to enable this ahead of time compilation as well, even though if you don't use it. And the second thing is that this whole ahead of time compilation only works on Linux systems, which brings us to the next JEP, which is going to be the most straightforward one. It's the JEP 317 called the Experimental Java-Based Just-in-Time Compiler. It was delivered in JDK 10, and basically what it allows you to do is it allows you to use Graal as a tier 4 compiler without building Graal from source, right? So it basically allows you to use the Graal that was there from the JDK 9, but this time you don't even need this whole ahead of time compilation thing. Okay, so it's basically there, and pretty much, because the Java 11 is the long-time support version, you can pretty much not care about Java 9 and 10 anymore, right? So take the Java 11, enable a couple of flags, and you have Graal. And now it also works for Mac and Windows. Alright, so we're pretty much finished with Graal. So you either need JDK 10 or let's say JDK 11, or you need a custom version of JDK 8 with all of this goodness backported, which brings me to the GraalVM. These days, GraalVM is just a fancy marketing umbrella term for a custom version of JDK 8 with all of this Graal goodness backported, right? So essentially with the Graal compiler. So if you wanted to take Graal for a spin today, if you're a typical Scala or Java developer like me, you have two options: either use the JDK 11 and enable of these two flags, or download the GraalVM, just put it on your path before Java, and you're good to go. All of these wonderful applications like IntelliJ or the Scala compiler, which is written in Java, SPT written in Java, Bloop written in Java, Ammonite written in Java, or Scala. It's essentially all bytecode, right? All of these things automatically benefit from Graal. Alright, we're pretty much done over here. Let me say a few more things before I leave in case you didn't fall asleep a long time ago. Number one, there is a reason why I bored you with all of these legal issues. The thing is that the proprietary version of Graal is even faster, so you might think about getting the Graal license at least for the development use, right? So at least for the desktop, which should be cheaper as the license which allows you to run Java on the server. Okay, to make you as productive as possible. Number two, GraalVM is a slightly bigger fish than what I just described. It is not just a JDK 8 with backported stuff and with Graal enabled. It also augments your standard library. It puts another library called Truffle on your class path, and this library can be used to call, for example, Python or JavaScript from your Scala applications, or you could even call some native C code with using technologies like LLVM, right? So for now, GraalVM is the JDK 8 was backported Graal stuff, and you have the Truffle, the library, which happens to be on the class path. Number 3, yet another part of the Graal VM is the so-called SubstrateVM, which is a meta-circular VM. Again, it just means that it's written in Java, and I believe, but I'm not sure, that it actually contains parts of the Maxine VM. Now, what is it for? Well, GraalVM comes with yet another tool called native image. And what native image allows you to do, obviously it uses Graal, the compiler behind the scenes, to compile your entire bytecode, right? So your entire application into this really cute tiny binary. But it actually also needs things like garbage collection. And so what it does is it throws out the JVM and it puts this SubstrateVM in there as a replacement, which is just like a minimal version, also written in Java, which doesn't really matter here, okay? So you have your entire application and you have the SubstrateVM put together, and what comes out is this teeny tiny binary which launches like a rocket. And by the way, the SubstrateVM also uses Graal behind the scenes because, as I just said, everything uses Graal these days. It's crazy. The typical caveats of ahead of time compilation and linking apply, right? So no dynamic linking, no reflections, etc., etc. There are workarounds for some of these things, like for example, you can have a config file where you specify all of the things that you're going to dynamically load with reflection, and then, you know, this whole native image thing will take these parts out and actually bundle them together, so it's actually going to work out. But in general, just beware that this technology is considered very, very experimental, even though the concept of ahead-of-time compilation is freaking ancient. By the way, even the enterprise version that Oracle commercially supports explicitly states that native image is not part of this whole agreement. Anyways, now we can finally arrive at the creme de la creme of Graal, which is ahead-of-time compilation. So you can take a Scala application, compile it ahead of time, a nice small binary comes out, and now you can deploy it on iOS, or at least in the near future you're going to be able to deploy it on iOS, because a statically linked binary means that there is no dynamic loading anymore, so Apple is happy. In fact, I'm going to have a link down in the description to the Scala Days presentation, I believe it was, where this technology is presented. In fact, there will be a lot of links down in the description, so this particular one is called Run Scala Faster with GraalVM on any platform. Yet another thing that native image allows you to do is to take something like the Scala compiler and compile it ahead of time, right? So now you have a Scala compiler which launches really, really fastly. It might be a bit slower though, so you should try it out and benchmark it for yourself. This is probably something that I should repeat. The purpose of ahead of time compilation is not to increase performance. It might still happen sometimes as a side effect, but you can't really expect that. Its purpose is to minimize the size of the application and also minimize the memory footprint at runtime. One other thing that sort of slipped through the cracks, again, there was so much information over here, is the project called Metropolis, which is an initiative to basically rewrite everything related to Java in Java. They call it Java on Java, right? So rewrite the Java compiler in Java, rewrite the JVM in Java, rewrite the garbage collection in Java, everything is in Java. And if that turns out to be successful, there are even more advanced experiments that they could do. And allow me to read something again. We could try to using Graal as a replacement for the client just-in-time compiler, right? So for the C1 compiler, using Graal to co-generate a bytecode interpreter, using Graal to spin adapters such as native to Java bindings, using Graal to dynamically customize other JVM hotpath, prototyping new JVM features such as value types in Graal, coding native methods in statically compiled Java, coding metadata access and processing in Java, coding smaller JVM modules in statically compiled Java such as class file parsing or verification, coding GC logic in statically compiled Java. Graal, Graal, Graal. Watch this video again and make a drinking game out of it. Drink every time I say Graal. It's another thing that I would like to mention, that at this point, Graal, the compiler, is pretty much stable, so it's very safe to take it for a spin, so please do so. However, everything else, everything else related to the GraalVM, the Truffle and the SubstrateVM or native image, they're pretty much still shaky. Also, it's a pretty well-known fact that A, Twitter is pretty much the biggest Scala shop on the planet, and B, they also heavily invested into Graal, and they even use the native image. So if they can trust it, you should probably take it for a spin as well. If you're interested in more in-depth talks about Graal, I'm going to have a few links down in the description, but essentially you can Google two names. The first one is Chris Seaton. He's an Oracle compiler guy, and the other one is Chris Thallinger. He's an ex-Oracle compiler guy, and now he's a Twitter compiler guy. And you can also follow the hashtag TwitterVM team on Twitter. Chris Thallinger in particular points out that the whole reason why Twitter is betting on Graal is that because it produces a more optimized code, and therefore you need containers with smaller CPUs, right? So you don't need bigger CPUs, and therefore you just save money. Another thing which is very important for Scala developers is that Graal works really well with Scala because it employs more advanced optimization techniques like partial escape analysis, which are really well suited for Scala because Scala programs tend to be more abstract, and therefore they tend to produce more structure. And so partial escape analysis leads to A, less garbage, and B, smaller graphs. And because you have smaller graphs, you also can inline more. But again, I'm not a compiler guy, so don't quote me on this. In any case, just to sum it up, these days there's pretty much no reason left not to use Graal, the compiler, as a tier 4 compiler. And again, as I already mentioned, on the other hand, the VM is still, the GraalVM is still a bit shaky, right? But you can still download GraalVM and, just use it as a replacement of the HotSpot VM. All right, I'm finally at the end of this madness. I have never done a video like this where I'm just talking. It took me like 3 hours to record this one video. Probably after editing, it's going to be like 40 minutes long or something, maybe even longer. I really don't know. In any case, it's been Vlad, devinsidey.com. Don't forget to like this video if you did, subscribe if you want to improve the developer inside you, and if you learned something today, consider supporting me on Patreon, and most importantly, take care.